This is chapter 3. We'll be talking about numerical descriptive measures. And so stick around. On this chapter, we want to learn how to describe the properties of central tendency, like variation and shape in numerical variables. We want to construct and interpret a box plot. So by the end of this chapter, you should be familiar with how to construct and what to interpret from a box plot. You should be able to compute descriptive summaries measures for a population, and finally calculate the covariance and the coefficients of correlation. All right, before we get started, let's define some terms that are important. When we talk about central tendency, what are we talking about? Central tendency is the extent to which the values of a numerical variable group around typical or central value. So you have a whole bunch of data, and you want to see where most of those values are. What is the central value of all the data that you have? And then the variation will be the amount of dispersion, basically how far away are those values from the central tendency. And the shape, when we talk about the shape, basically we're talking about how distributed are those values from lowest to highest. Where do they rank? How do they fall into place? And if you were to put them in a shape, where will they be? So imagine, for example, that you took a math test and you scored 79, and you're very disappointed because you are an A student and you only scored 79 on this test. But then you find out that the mean or the average for this test was 47. Say, wow, I did very well. So that will be your central tendency. Most of the people, if you add all the scores of everybody who took the test, the average was 47. The mean was 47. So that tells you that you did very well compared to the rest of the students. Now the variation will be how close are people to the 47 mark. Maybe most people did really, really close to the 47, so they scored 48, 50, maybe 51, or 42 and 43. So that tells you the variation, how close they are to the central tendency, the mean that you found. And finally, the shape will be how you are distributed once you add all those values. Once you put those values into place from lowest to highest, that will give them the shape of the data. And we'll talk a little bit more about that. Let's talk about the mean. So average people call mean average, but because we're statisticians, and we are going to call the average the mean, not because we're mean, but because we're not average. Okay, so what does this mean? Basically, average and mean are similar, but they're different. A lot of people think the average and the mean are the same thing, but they're not. Basically, the term average is the sum of all the numbers divided by the total number of values in the set. You already knew that, right? You add all of the numbers, you divide it by the quantities that you have, and that'll give you your average. But the mean basically is finding the average of a sample data. So average is finding the central value in math, where means is finding the central value in a statistic. Basically, we use the average when the difference between the values is less for the set of values that have more difference. So we prefer to find the mean of the data. What this basically saying is that there are different type of means, and we'll talk a little bit more in a minute. But the mean is pretty much like the average, but there are different types of means. So all of the average are mean, but not all means are average. And we'll see why in just a minute. Okay, so how do you calculate the mean? I'm pretty sure most of you guys are very familiar with the average. On this class and in statistics, we don't use average. We use what is called the mean. And it is going to be the most common measure of central tendency. That's something that most people use and most familiar is what it is, right? So you add all of the values that you get, and then you divide it by the number of values. Really simple. The problem with the mean is that it is susceptible to extreme values. So look at this example here, right? You have one value of 11, one value of 12, 13, 14, and 15. So your mean is going to be 13, right? You add all of those values, gives you 65. You divide it by the number that you have, which is 5, and then you have a mean of 13. But let's say that instead of having a 15, you get a 20, and see your mean just change. Now your mean, instead of being 13, now it's 14. Just because one value changed, it affected the mean of the data that you have. So that's one of the deficiencies that the mean is affected for extreme values, the outliers. So in order of array, so you add the values from lowest to highest. The one that is right on the middle, that's to the one we call the median. So look at this one here. You have the same data that we had on the past from 11 to 15. Your median is 13 because that is the value that's right on the middle. If the last value changes like it did on the last one from 15 to 20, your median is still going to be 13. The advantage of the median, it is that it's not affected by extreme values. So you can have 100 and your median will not change. Your median is still going to be the same number. So on the median, again, you put your numbers, your values from lowest to highest or highest to lowest, it doesn't matter. And then you find the number that is right on the middle. So to locate the median is really simple. We have this formula. The median position is going to equal the number of observations that you have plus 1, and then you divide that by 2. If the number of values are odd, then the median is going to be the middle number, like on the one we have, right? We have 5 observations. The median is always going to be the bottom number. So what would happen if we have 6 observations rather than 5? Then you don't have a number that is exactly on the median. So what you do in that case, you do the same formula. You add 1 to the numbers of observations that you have. You divide by 2, and then the value is not going to be on the median, but it's going to be the position in the ranked data. It's really simple, right? It's going to be the average of those two middle numbers. So if on the case we have 5 observations, now let's say we have 6, so you will add the numbers between the third and the fourth observation, because those are two right on the middle. You divide by 2, and that is going to be your median. On that case will be 13.5. Another measure of central tendency is what we call the mode. So what is the mode? Basically, is the value that occurs the most often. Good thing about this thing is that it's not affected by extreme values. So you could have your data, and then you could have like one outlier out there really high, but it will not affect the mode. And is used for either numerical or categorical data. Thus, you can use it for either one. And in some circumstances, you could have no mode, because you could have all of the values are different, and there is now one that occurs most often. So you could have a data where you have no mode, or you could have a data that will have several modes. So you have different data, and there are like 2 values that appears um, about the same time, same amount of time. So at that time, you can say, we do have 2 different modes. So look at this example here. You have one value at number 1, one value at number 3. You have 2 values at number 5, and then you have 3 values at number 9. So that will be your mode, because number 9 is the one that appears the most. And the one on the right, you have the values from 0 to 6, and all of them just appear one time. So in that case, you have no mode. Let's say on the example on the left, if you have 3 number 5s, 3 number 9s, and 3 number 12, you could have 3 different modes, 5, 9, and 12. So again, the mode is just the value that occurs the most. Okay, here is an example. On this one, we're looking at home prices. We have the highest price at $2 million and the lowest price at $100. So on this case, you add all the prices, you divide for the number of houses that you observe, and that will give you $600,000. So you can say the middle value of ranked data is the mean will be $600,000, right? So you say, wow, the homes are really expensive on this area, because the mean price is $600,000. But in reality, when you take a look at it, there are 2 of them that are at $100,000. So you could still get an affordable home at $100,000 and not think, oh, I have to get a loan for $600,000 because that's the mean on this area, right? The median will be the value that is ranked, that is rank in the middle of the data. On this case, because we have 5 observations, that will be the one right on the middle, which is the $300,000. So that will be the median price. Now the mode is the one that appears most frequent, and you can see that will be $100,000 because that appears twice. So based on the mode, you can say, yeah, you know what? Most of the houses here, the one that appears to show the most is $100,000. So you say, yeah, I could probably afford a home over here. So how do you know which one to use? Which is the best central tendency to use? I guess it all depends what you're trying to achieve. The mean, you will probably use it, is the one that is used the most. That's the most frequent one. That's the one that people are more familiar with. And unless you have extreme values, you should probably use the mean. And if you do have a lot of extreme values, you can probably remove those extreme values and figure out, you know what, we're going to reduce extreme values because they don't really represent the data, and you could do that. The median is often used since the median is not sensitive to extreme values. That's kind of good thing to use the median. Home prices may be reported for a region. It is less sensitive to outliers, so you don't have to worry about the same thing that you do with the mean. In many situations also, it might make sense to report your data, both mean and the median. So sometimes you're probably going to say, yeah, this is the median, this is the mean. That way you can get the full picture. So there is another type of mean that we call the geometric mean and the geometric rate of return. So what does that mean? The geometric mean is different than the mean or the average that we talked about it. And basically, it is good to measure the rate of change. And geometric mean of change, we can see the formula here. We have x bar of g is going to equals the x1 plus x2 plus xx's, and then you elevate that to 1 divided by the numbers of observations. And this is good when you want to measure the changes on rate of returns over time. And here we have the R bar of G is going to equal 1 plus the rate of the first period times 1 plus the rate of the second period, and so on and so forth. And then once again, you elevate 1 to the numbers of observations, and then you subtract 1 from that. So imagine that you bought 2 Bitcoins, and then you bought them at $50,000 each. So you had $100,000 laying around. So you know what? I'm gonna buy 2 Bitcoins. And at the time you bought it, the price was $50,000 each. So you spend your $100,000, right? And then the crypto market crash, and the price of the Bitcoin went down to $25,000. So the $100,000 you invested on those 2 Bitcoins, now it's only worth $50,000. But then the market rebound, and it's go back to $100,000 by the end of the second year. So now you have your $100,000 back. So you might want to ask, what is my rate of return? And if you were to use the average, you will get a different number. But if you were to be realistic, you can see that from 100,000, that's when you started, and then prices went down, so you're down to $50,000. So you had a 50% decrease. But then it went back again, and now you're back to $100,000 for the second year, and then you get 100% increase. So overall, 2-year return is 0, right? Because you're at $100,000. That's what you started with, and you ended up at the same level. So if you use the 1-year return to compute the arithmetic means, you will get this right here. So you have that x bar, right? And on the first year, you lost 50%, so you have negative 0.5. On the second year, you gain at 100%. So if you add those two and then you divide it by 2, that's how you will normally do their average or the arithmetic mean. You will get 25% rate of return, but that's lying. You still got your $100,000. You didn't make any money. So that's where you will need to use the geometric mean. And the geometric mean, which is R bar, you have 1 plus the rate of return for the first year times 1 plus the rate of return for the second year, and then you elevate that to 1 divided by the numbers of observation, and then you subtract 1. That's where you get your actually rate of return. So in this case, you will add 1 plus negative zero point 0.5. That'll give you 0.5. And then you multiply by 1 plus 1, which is 2. So you multiply those two, and then you do it to the half power, and then you get that down to 0, which is actually what you got because you started with $100,000. You ended up with $100,000, so you didn't gain any money, you didn't lose any money. Your geometric rate of return will equal 0. So you see the advantage between using the geometric rate of return compared to the use the arithmetic mean, which are different. All right. In a short, let's talk about central tendency. Let's summarize what we just talked about it. We do have the arithmetic mean, where you add all of the values and then you divide it by the numbers of observations that you have. We have the median, which is the middle value in the order of array, which the good thing about this is not sensitive to outliers, to having those extreme values. So the median is not affected by that. Mode is the value that shows up more frequently on your observations. You can have 1, you can have more than 1, or you can have 0. And then you have your geometric mean, which is your rate of change for a variable over a period of time. So you need to know which one to use based on what you're trying to achieve. Now let's talk about measures of variation. So again, going back to the beginning of the chapter, right? What we mean by variation, right? How much change there is. So there are different ways to measure variation. One is the range, which we talked about on chapter 2, remember, where you add your highest value, you subtract the lower value, and that'll give you your range. And then you have your variance, which is the change, how much change there is. Then you have your standard deviation, and then you have your coefficient of variation. So measures of variation give information on the spread. So how far apart are these values, or the variability, right? Or the dispersion of the data. So how spread out is the data or these values that we're talking about. So that's what we're trying to measure when we talk about variation. Again, at this point, I think we're all familiar with the range. Is the easiest mode of variation. Basically, you get your the largest value, you subtract the smallest value, and that'll give you your range. We saw that on chapter 2. In this case, you have your highest value is 13, your lowest value is 1, so 13 minus 1 is 12, and that will be your range. So your range will be 12. This could be misleading because you are not taking into account how the data is distributed, right? How much data there is. Maybe most of the data is towards 11. Maybe most of the data is towards the bottom. You don't know. Also, another thing about the range is sensitive to outliers. So you can have all of these values that are really low, and then you have one value that is really high, and that will change. Look at this example here, right? You have several values that are 1, and then you have value that is a 5. So your range is 4. You can say, yeah, my range is only 4. Okay. But what if you have one value that is 120? So all of a sudden, you have your range going from 4 to 119 just because one value changed. So in that sense, the range could be misleading. But again, it's the simplest way to measure variation. Now, let's talk about the sample variance. Basically, what we're trying to do with the sample variance is basically get the average of the square deviations of value from the mean. And here is the formula. So you have your sample variance is going to equals the sum of the values of that value minus the mean, and then you square that and you divide by your numbers of observations minus 1. And that is the formula for the sample variance. And then the sample standard deviation is the one that you're gonna mostly use, that we're gonna use most of the time. The good thing about this, it shows variation about the mean. So how much change are from these values from the mean. And it's just the square root of the variance. So you already know how to calculate the variance. All you have to do is take the square root of your variance, and that will be your standard deviation. And this data will be on the same type of unit as the original data. So if you're talking about dollars, will be dollars. If you're talking about cubic feet, it will be cubic feet, and so on and so forth. So the same unit of measure that you have from your original data, that is the one that you will have on your standard deviation. Here are the steps for computing a standard deviation. Basically, you compute the difference between each value and the mean. And then what you're going to do, you're going to square each difference. Then you're going to add the square difference that you just got. And then you divide by n minus 1 to get the sample variance. And all you got to do is take the square root of the sample variance, and that will give you your standard deviation. So 5 easy steps to get the standard deviation. So here we have an example. Look at your data. You have 10, 12, 14, 15, 17, 18, 18 again, and 24. So you have 8 is your numbers of observations. If you add all of those numbers and you divide them by 8, you will get 16, which is your x bar or your mean. And then all you gotta do is subtract each value from 16, and then you square the value, and that will give you your, and then you get the square root of that, and that will give you your standard deviation. In this case, it was 130 divided by 7, and then you square root of that, you get 4.30. And it's a measure of the average scattered around the mean. So your mean is 16, and then how far from the mean each are those data is separated from. So you can say, yeah, my mean is 16, my standard deviation is 4.30. So one standard deviation will be 4.30 from the mean. So let's take a look at this. So here, look at this data here, right? You have these values, and so your mean is 5.5. Your standard deviation is 3.38. Data B, you have similar data, and the mean is 15.5. So once again, you get your mean 15.5, but see, your standard deviation is 0.926. The reason is because here you can see how most of the data is around your mean. So your mean is right over here, right? And then most of the data are going to be around that mean. On this one, the standard deviation is higher because your mean is right over here, but you guys can see how spread out the data is. You have 111, you have a 21. On this one, the lowest number is 14, the highest number is 17. Now take a look at data C. Your mean is still 15.5, but your standard deviation is 4.56 because the data is spread out towards the outliers. So you can see how much spread out the data is, and that's what the standard deviation is telling us. Here is an example, kind of the same thing. You see the smaller standard deviation, you see the shape of the curve, and then when you have a larger standard deviation, the curve is more flat. So going back to this, if on this one here, you guys can see how this is flatter. This one will be less flatter, right? This will be more shaped like this. And this one, the shape will be kind of weird because it will go from here to there. So you guys can see how the shape is kind of telling us where the standard deviation is. Okay, let's summarize what we talked about so far, right? The more the data are spread out, the more that is all over the place, the greater the range, variance, and the standard deviation. We saw that when the standard deviation is 4.6, the data is all over the place, right? The more the data is concentrated, then you're going to have a smaller range, a smaller variance, and a smaller standard deviation. So that's just telling you how spread the data is. If the values are all the same, there is no variation, then the measure will be 0, right? Because, you know, everything is right on the middle. Let's say all of your data is 15, then you have your average 15, your mode will be 15, your everything will be 15, and then these values for the standard deviation, the variance, and the range will be 0. And just remember, so never can these values be negative, right? You cannot have a negative standard deviation. You cannot have a negative range because, you know, if your highest value is 120 and your lowest value is 120, then you're going to have 0. You cannot have your lowest value be higher than your greatest value because then they will be opposite, right? So these measures can never be negative. Just remember that. Uh, what about those measures of variation? So now we know, right? They're spread out, but how much spread out they are, and that's what we have those measures of variation. And the first one is the coefficient of variation. Basically, it measures relative variation. This measure, the coefficient variation, is always going to be in percentage, and we'll see why in just a minute. Uh, and it's telling you how variation is related to the mean. So you have your mean and how much change are from one value to the next. That's the only thing the coefficient of variation is measuring. Can be used to compare the variability of two more sets of data measured in different units. And we'll see an example on the next slide. But the reason is always in percentages because of this, because you can have your coefficient values and you're going to get your standard deviation and you're going to divide that by the mean, then you multiply that by 100%. And that's why it's always in percentage, because you're multiplying by 100%. Okay, so you bought two stocks, right? Or you bought a Bitcoin and you also bought Ethereum, and you're trying to figure out, which one is making you the most money. So you get the mean price last year, right? Remember, it was $50,000. On this case, we're gonna simplify it to say 50, and then you get your standard deviation is 5. So your coefficient of value um, is going to be your standard deviation 5 divided by the mean, which is 50, and then you multiply by 100%, and that'll give you 10%, right? That's your coefficient value. And then you have your Ethereum, which let's say that it was the mean price was $100. Your standard deviation is 5. So in this case, you divide 5 by 100, you multiply by 100, you get 5%. So you can compare how your Bitcoin did compared to your Ethereum. So even though they had different prices, now you can compare to see which one give you more rate of return for your money. In this case, you can say that Ethereum is less variable relative to the mean price that you pay for Ethereum. Uh, Here we have two stocks, right? So we have a stock A, which we already did, and we know it's 10%, and then we have a stock C, which the mean price last year was $8. Your standard deviation for the stock was $2. So here you have $2 divided by 8. You multiply by 100, you give 25%. You can say that stock C has a much smaller standard deviation, but it has a much higher coefficient of variations. So that is a really good way to figure out which one is giving you the higher variation. One thing that you really need to pay attention to is the z-score. So what is the z-score? Basically, the z-score of a value is the difference between the value and the mean divided by the standard deviation. So if the z-score is 0, then the value is equal to the mean. If the z-score is positive, then it's above the mean. If it's negative, it's below the mean. So that's something you need to keep in mind, the z-score, right? If you have 0, then you know you are equal to the mean. If it's positive, you're above the mean. If it's negative, you're below the mean. And this z-score can help you find out extreme outliers. So you compute the z-score of a data value, then you subtract the mean, and then you divide that by your standard deviation. And the z-score is going to be the number of standard deviations of data values from the mean. This is very important. If you have any value, any z-score about 3% or below, I'm sorry, not percentage, but you have a z-score about 3 or below or negative 3, then you know you have extreme values. And we'll see that later in this chapter why those extreme values are there. But just remember that for now. Anything about z-score about 3 or negative 3, then it is an outlier. And then something you may want to take a look at it. The larger the absolute value of the z-score, then the farther away you are from the value of the mean. So the higher your z-score that you get, then you know you are farther away from the mean. Going back to the example that we talked about at the beginning, where you guys scored a 79, you were disappointed. but you know you got a C-score of 3.5, that telling you that you did well above everybody else on that test. So the C-score can tell you how far away you are from the mean. Here's the formula to calculate the C-score. You grab the value minus the mean, and then you divide that by the standard deviation, and that's how you get your C-score. Okay, so let's take a look at this example. Imagine that the mean for an SAT in math is 490, and the standard deviation is 100. So to compute the C-score in this case, for a test score of 620, what you gotta do is you got the 620 minus the mean, which is 490, and then you divide that by the standard deviation, that is 100, and then you get 1.3. So if you score 620 on an SAT, you know you're 1.3 standard deviations above the mean, and it's not considered an outlier. To be an outlier, you have to be C-score of 3 or more above. Here is the shape of a distribution, and basically a shape is just telling you how data is distributed. So you could have the bell shape, you can have different ways. There are two useful shapes that you need to keep in mind in a statistic. One is the skewedness. So measure the extent to which data values are not symmetrical. Skewedness just tell you how symmetrical those values are. And then you have your kurtosis, which measures the thickness of the curve of the distribution. So how sharply the curve rises approaching the center of the distribution, basically how flat it is, the data. Let's take a look at some shapes that explain that. Here in this case, we're talking about the shape of distribution, the skewedness. So once again, we are measuring to which extent the data that we're looking at it is symmetrical. So if you look at the first example, we can see that one is left skew. So the mean is less than the median. Remember those two values that we found, right? The mean and the median. So if the mean is less than the median, you're going to have a less skewed data. If the mean equals the median, then it's going to be symmetrical. So that's when you have those bell-shaped curves. And then if your median is less than the mean or the mean more than the median, whichever way you want to look at it, doesn't matter, then you're going to have a right skew. So your skew is going to be right because your median is going to be less than the mean. Now the kurtosis just means, right, remember how much the data is closer to your mean. So you can have a sharper peak, okay, that's more than the bell shape, and we call those leptokurtic. Basically what you're saying is that your kurtosis is higher than 0. You can also have the bell shape, which means your kurtosis equals 0, and we call that mesokurtic. And then you have the flattened and bell shape, and in that case, you see the kurtosis is less than 0, and we call those platykurtic. Another measure that you can use is what we call the quartiles, and that is very helpful to visualize how the data is being distributed. So you can use quartiles, you can use the five number summary, and you can use the construct a box plot. So let's see what this means. So quartiles, basically what you're doing is you're grabbing all the data and you rank into 4 segments, and you put an equal number of values per segment. So think about like a year, right? You have your year, and usually your year is divided in quarters. So the first quarters will be January, February, and March. Second quarter will be April, May, and June. So it's kind of the same thing when you come to quartiles, right? You're grabbing all of the data, and then you divide it into 4 segments, and then you have your first quartile, which is going to be the 25% of all the values that you get. So it's going to be less than the 75%. So the other 75% of the data are going to be on the other 3 quartiles. But then this is your quartile 1. Now, the second quartile is going to be the same as the median, which means 50% of the values are smaller, and 50% of the values are larger. That's right on your middle. And then only 25% of the values are greater than the third quartile, right? That's only the fourth quartile will be greater the uh, than the third quartile. So how do you locate those quartiles? We do have a couple of formulas that will help you with that. To find a quartile, determine the value in the approximate positions in the rank data. So the first quartile, you have the numbers of observation plus 1, and then you divide that by 4. You just got to make sure your values are ranked from lowest to highest. The second quartile, you do the same formula and the numbers of observation plus 1, and instead of dividing by 4, now you divide by 2. Once again, your values have to be ranked. The third quartile is a little bit different. You have 3 times the numbers of observation plus 1, and you divide that by 4. Once again, your values has to be ranked. And then n, obviously on this formula here is the number of values that you observe. You have to keep in mind that when you're calculating these rank positions, you have to keep a few rules in mind. One, if the result is a whole number, then it is the rank position that you are going to use. So if the result is a fractional half, then the average of the two corresponding data, you're going to use the value of the two corresponding data values. And finally, the other rule to keep in mind, if the result is not a whole number or a fractional half, then you need to round out the results to the nearest integer to find the rank position. Let's look at an example to make sense of this. So here is your data, right? And then you are rated in order from lowest to highest. So you have 11, 12, 13. You have two 16s, 17, 18, 21, and 22. In this case, we have number 9 is going to be the numbers of observation that we have. So to calculate the first quarter, you take n plus 1, that will give you 10. You divide that by 4, and then you get 2.5 positions of the ranked data. So in this case, your Q1, your quartile, your first quartile is going to be 12.5. 12 plus 13, that'll give you 25. You divide that by 2, that will give you 12.5. The second quartile is going to be 9 plus 1, 10 divided by 2. That'll give you 5. So it's going to be the fifth position. So you take 1, 2, 3, 4, 5. So your median is going to be 16. So this is your right on the middle, right? This is your second quartile. To get the third quartile, we once again, we had 9 plus 1 that gives us 10. 10 times 3 is 30 divided by 4. It will give you 7.5 positions for the rank data. So we have to look for the 7 and the 8 position, and then we add them and we divide that by 2, and that will give us 19.5. So Q1 and Q3 are measures of non-central location, right? Because they're not in the middle. While Q2 is the median, right? It's a measure of central tendency. Just keep that in mind. Let's talk about the interquartile range. What is the interquartile range? So that's where the IQR is Q3 minus Q1, and basically it's just measuring the spread in the middle, or the 50% of the middle of the data, right? The interquartile range is also called the mid-spread because it's covering 50% of the data. So it's the spread in the middle. The IQR, or interquartile range, also measures variability that is not influenced by outlier. Remember, because you're only taking the data right on the middle, so you're not affected by those extreme values that could be towards the ends. So measures like Q1, Q3, and IQR are not influenced by outliers, are called resistant measures. So that's how you will call this interquartile range. Let's look at an example. Here you have your Q1, right? And you have your X, your minimum. In this case, remember, you will have your range will be 17 minus 12. But what we're looking here is a interquartile range, which is the data right over here on this 25%, right? So you have the 30 and the 57. So your interquartile range, in this case, the lowest value, 57, minus your lowest value is 30. So the range for the inner quartile is 27. Here is the 5-number summary. You need to pay attention to this because you will need it for the project that we will be doing. So basically, those are the 5 numbers that help describe the center spread in shape of data. So you're going to have your smallest value, you're going to have your largest value, you're going to have your first quartile, you're going to need your median, and then you're going to need your third quartile. So you have Q1, Q2, Q3, your smallest and your largest value. Let's talk about the relationship among the 5-number summary and the distribution shape. So if it's left skew, that means the median minus the smallest value is going to be higher than the largest value minus the median. Q1 minus the smallest value will be higher than the largest value minus Q3. The median minus Q1 will be higher than Q3 minus the median. Remember the less skew example that we saw a couple of slides ago. If you grab those data, that's how it's going to fall. Symmetric, right? When you have the bell shape and it's symmetric, that means the median minus the smallest value is going to be roughly equal to the largest value minus the median. It just makes sense because it is symmetric. And then you have the Q1 minus your smallest value is going to be equals roughly to the largest value of X minus your Q3. And finally, your median minus Q1 is going to be more or less the Q3 minus the median. If it's right skew, it's kind of the opposite to the left skew. You have the median minus the smallest value that you have is going to be less than the largest minus the median, and the quartile 1 minus the smallest value of X is going to be less than the largest value minus Q3, and then the median minus Q1 is going to be less than the Q3 minus the median. Here is 5-number summary and the box plot, right? The box plot, basically, what is a box plot to begin with? Let's talk about the box plot. Box plot is nothing but a graphical display of the data based on the 5-number summary. So remember the 5-number summary, right? You have your smallest value, you have your Q1, you have your median, which is your Q2, and then you have your Q3, and then you have your latest value. So look at this example here, right? Here is your smallest value. Right over here, you have 25% of the data. That's your Q1. And then you have your median, which is, remember, that's your Q2, right? 25% of the data. So once you're here, right, you're right on the middle. And then you have your 25% of the data for the Q3, and the last 25% of the data, which is your Q4, and that's where you find your largest values. So if the data is symmetrical, then the box plot central line are centered right between the endpoints. In this case, all of your data is symmetrical, so you see how everything looks perfect. Both sides are exactly the same. A box plot can be shown in either a vertical or horizontal orientation, so it doesn't matter which one. I personally like it when it's a horizontal position, but you can use either orientation will work. So if you have a less skew data, like we talked about it, you can see how the box plot is represent that, and you see how the right side is smaller than the left side of your box plot. That's because most of the data is going to be towards the left, right? Remember that symmetrical, once again, the box plot in this case will be, both sides will be the same, the right and the left. Finally, if it's the right skew, then your right side of the data here of your box plot is going to be bigger than the one on the left. Okay, let's take a look example to put this into perspective. Here is a box plot for the following data, right? So your smallest value is 0, your Q1 is 2, and then you have your median will be 3, and your Q3 will be 5, and your largest value is 27. And you can see how this data is right skew, right? And then the box plot represents just that, because most of your values are going to be towards the lower numbers, 0, 2, 2, 2. 27 is an outlier, and you guys can see that very clearly in this box example. 27 is way out there compared to where the rest of the values are. And you guys can see how the right side of the box plot is higher than the left side of the box plot. All right, let's move on and let's talk about numerical descriptive measures for a population. So descriptive statistics discussed previously basically is just talking about a sample, remember, not at the entire population. So if you were doing a study of Rocky Meadows Community College and then you don't have the ability to look at all 12,000 students, you're only going to grab 1,200, right? So that's what we were talking about, those samples. But if you could do the entire population? Let's say you just want to take a look at your classroom, right, where you have 20 students, and you could definitely do a study of the 20 students. So in that case, you will be doing the entire population. And the summary measures describing the population, we call those parameters, and we use the Greek letters to represent those. Important population parameters will be the population mean, the variance, and the standard deviation. Just like the ones that we learned from the sample population, now we're going to use those same measures for the entire population, the mean, the variance, and the standard deviation. So what you need to know is we use different letters, so that way you know whether you're talking about a sample of the population or you are talking about the entire population. In this case, the population mean is represented by the Greek letter mu, and the population mean, it will be the same. You sum all the values in the population, and then you divide it by the population size, which is in this case, remember the other one was a small n. On this one, we're using the big N to represent the entire population. So here you have your population mean is going to equals the sum of all the values divided by the size of the population. And the variance will use once again, we'll use the Greek letter called sigma, and that will be sigma squared. Remember how we square the values, right? So you're gonna get the value minus the mean, and you're going to square those, you're gonna add them, and you're gonna divide it by the numbers of observation that you have. In this case, is the entire population. So you have your population size, you have your population mean, and then you have your numbers of values. And you have your standard deviation. In this case, we're gonna use sigma, and sigma is basically the square root of the deviations. So this is the one that you're going to use most of the time to measure variation, because it shows variation from the mean and will be the square root of the population variance. And here you have the standard deviation is going to be the square root of the variance. One thing you need to keep in mind is going to have the same unit as the original data. So if you were talking about dollars, you will continue to talk about dollars. If you were talking about Celsius, you continue to talk about Celsius, or Fahrenheit, or whatever measure you were using, it will be the same units. Just keep this in mind for population versus parameters. So you have your mean. If you're talking about the population, you will use mu. If you're using sample for the sample statistics, so you only have a portion, then you're going to use x bar. Then you have your variance, and then you have your standard deviations. Now, let's talk about this empirical rule, right? In most data set, a large portion of the values tend to cluster near the mean. In a right skew data set, the cluster occurs to the left, and on the right skew data, and in a left skew data, most of those values are going to be to the right of the mean. In the data is symmetrical, then the median and the mean are the same, and the values tend to cluster around the median and the mean, producing a bell-shaped distribution, which we also call a standard distribution. One thing that you will see is 68% of the data in a symmetrical mound-shaped distribution, or the bell shape, the standard shape, is within one standard deviation of the mean. So the mean is going to be plus minus one standard deviation. So here you see that how 68% of all the values are going to be around your mean. Continuing with the empirical rule, you're going to find out that 95% of the data in the symmetrical mound-shaped distribution, which is also called bell shape or standard shape, lies within two standard deviations of the mean. So 95% of all the data that you have is going to be around two standard deviations from the mean. And finally, 99.7% of the data symmetrical mound shape are between three standard deviations. So remember how we talked earlier about being about three standard deviations? That means out of 1,000 observations, only three of those will fall above three standard deviations. So in the case of where you score 79 on the test and you are 3.5 standard deviations above the mean, that means that you out of 1,000 people that would have taken the test, you score on the, you're one of those three people that score higher than the rest of the 997 other people who took the test. So here's an example about the empirical rule. Let's say that you the variable math for an SAT score is bell-shaped, and the mean is 500, standard deviation is 90. Then you have that 68% of all the people who are taking the test are going to score between 410 and 590 because your mean is 500 plus minus 90. Then you have your then you have 68% of all those people are going to fall between 410 and 590. If 95% of those test takers are going to be between 320 and 680, that's where you get your 500 plus minus 180, two standard deviations, right? And finally, 99.7% of all people who's taking the test are going to be between 500 and plus minus 270. That'll give you 230 plus 770. So in order to be that 3%, or I'm sorry, 0.03% or 3 out of 1,000, you will need to score lower than 770, or you can also score lower than 230. So only 3 out of 1,000 people are going to score lower than 230 or higher than 770. But what happens when the data is not bell-shaped? Then you can use the chebyches theorem or the chebyches rule. And basically, this is saying that you can estimate the minimum proportion of observations are going to be between the specific number of standard deviations from the mean. So it doesn't matter what shape does that curve has. It could be the bell shape, it could be skew to the left, to the right, doesn't matter. Basically, this rule is saying that the numbers of observations are going to be equal to 1 minus 1 divided by the standard deviations square times 100. So while this might look complicated, it is not. It's really simple. The only thing you need to keep in mind that the standard deviation has to be higher than 1. If you do it for 1, it's not going to work. But let's say that you want to do it for 2 standard deviations. So you have 1 minus 1 divided by 2 squared or by 4 times 100. That'll give you 75%. So you can say that the numbers of case is going to equal 2 times times the mean plus minus 2 standard deviations. And then if you want to take 3 standard deviations, you have that 88.89% of all the observations are going to fall between 3 standard deviations of the data that you have. So, so far we have discussed the measures of relationship between two numerical variables. You have the scatter plots that allow you to actually see, put that into perspective, visually see, and examine the relationship between two numerical variables. And now we can talk about the two measures that tells you how far the relationship is. So the covariance and the coefficient of correlation. What is the covariance? Basically, the covariance is just telling you, is just measuring how related is one value to the other. So how strength are in a linear relationship of two numerical variables. In this case, let's talk about x and y. So you have your sample covariance, you have the covariance of x and y, and that is going to equal to the sum of x minus x bar, which is the mean, and then y minus y bar, which is the mean of y, divided by n minus 1. Now, the only thing that we're looking at this is to see how strength is that relationship. And then there is no causal effect is implied. So you're trying to figure out, I have a data that shows me the score that this student got receive on a math test and the score that they receive on a chemistry test. And you want to see how correlated it is, how well the people did in math, how well they did in chemistry. So there is not saying that if you do well in math you're going to do well in chemistry, or if you did well in chemistry, you're going to do well in math. The only thing you're looking at is saying, how correlated those two data are. So remember, doing well on one does not imply that you're going to do well on the other. You're just trying to find out how strong the relationship between those two variables are. So if you have the covariance between x and y is higher than 0, then you're trying to see that y and x, they both of them tend to move on the same direction. So after looking at data, you find the covariance, and the covariance is higher than 1. You can say, yeah, people who do well in math tend to also do well in chemistry. If x and y is less than 0, then you can see that they move in opposite direction. Basically, what you're saying is people who do well in math tend not to do well in chemistry. People who do well in chemistry tend not to do well in math. And then if x and y equals 0, then you can say, there is no correlation between doing well in math and doing well in chemistry. We cannot really say that people who do well in math are going to do well in chemistry or vice versa. One of the major flaws that covariance has is doesn't tell you how strong the relationship is based on the size of the covariance. That's something you need to keep in mind, that you're not saying, oh, you know what, this is there is a strong correlation. It's just telling you that there is a covariance. Now, the coefficient correlation, basically this one is measuring the strength, so how strong the relationship is between two numerical variables. And the sample coefficient of correlation is going to be R, and then you have the covariance of x and y that you already find out, divided by the standard deviation of y and the standard deviation of x. So the formula that you have here at the bottom is something that we are familiar with, it, something we've been looking into it. You have your covariance formula that we use. You have your standard deviation for x, which is nothing but the variance, right? The sum of x minus the mean squared divided by the numbers of observation minus 1. And the third part is the same thing, but is for y. So here you have your standard deviation for y. So nothing really that we haven't seen before when you talk about coefficient of correlation. Some of the features that we get from the coefficient of correlation is that the population coefficient of correlation is referred as P, and then the the sample coefficient of correlation is referred as R. Either P or R have the following features. They're unit-free, so you're not talking, right here, you're not talking about units of measure, so you're not talking about dollars, you're not talking about centigrades, you're not talking about square feet or anything like that. The range is going to be -1 and 1, so your efficient correlation is always going to be between -1 and 1. The closer you are to -1, the stronger the negative line relationship is. So imagine that you have a -0.9 between the math test and the chemistry test. You can say, yeah, the better you do in math test, the worse you're going to do on the chemistry test. If it's closer to 1, then you can say the better you do in chemistry, the better you're going to do in math. If it's closer to 0, then you can say there is no weaker relationship. If it's 0, you can say there is no relationship at all. So here is an example to put this into perspective. Look at the first one, right? You have R equals to -1. So that's why you see this one is downward sloping. And you guys can see how this is very related. Everything falls straight into the line. And this one is -0.6. So once again, it's downward sloping, but you can see how the points are not exactly on the line, but they are somewhat close to it. On this one here, your correlationship is positive 1, so that's why it's upward sloping, and all of the points fall perfectly in line with a line. 0.3, you can see how the data is kind of spread out, but not too far out. And finally, when the coefficient correlation is 0, on this case, you have a perfect horizontal line, and all of the points are there. Couple of things you need to keep in mind. Some of the pitfalls that you're going to have when talking about numerical descriptive measure is data analysis is subjective. Should report the summary measures the best descriptive and communicate important aspects of the data set. And finally, the data interpretation is subjective, right? Should be done in fair, neutral, and clear manner. A lot of the things you have this data, and then the people that interpret it are not being subjective. I do see a lot, especially in politics, say, hey, we have this, and this is what it means. Because you are being subjective, you're just telling us what you mean. Okay, so that's something you need to keep in mind. So numerical descriptive measures should document both good and bad results. So you don't want to say just only the good, because that's what promotes your agenda. You want to be fair and tell them what good and bad results that you got. You should present it in a fair, objective, and neutral manner. And that's something that is really hard, because you may be passionate about something, so you want to steer people your way, but that's not ethical. And finally, you should not use inappropriate summary measures to distort facts. Just present the facts as they are. Okay, to summarize this, we have discussed describing the properties of central tendency, variation, and shaping numerical variables. You should now be comfortable constructing and interpreting a box plot. You should be able to compute descriptive summary measures for a population, and you should be able to calculate the covariance and the coefficient of correlation. All right, thanks for listening.